Hi, everybody. Welcome to day 3 of AFRICAST. I hope you enjoyed the first 2 days. So today is quite important because we'll start doing um, a part of like Fable ecosystem where you can fit models and produce the forecast. And actually, it is getting like more exciting because you'll see some outputs that you can use your own work as well. So we will have 2 sessions. The first session I'm delivering it is about basic modeling and forecasting. And the second session, we will move on to talk about time series um, forecasting using regression, and Mitch will deliver that one. So what we have for the first session? Well, first of all, we start by revising the definition we had for forecasting. So in the first day, we started with the definition of what we mean by forecast. Here, we look at that, but we also provide a more accurate definition of forecast, or statistical forecast, I should say. And following that, because we're talking about forecasting, it's important to know what can we forecast. Because in your own work, you may have many possible variables that you want to produce forecast for, but there are some criteria that we need to be aware of when it comes to if this variable that I'm interested in can be forecasted accurately or not. This is a topic we call forecastability. So we will cover this a little bit as well. And after this, we go and talk about some benchmark methods, and we have to also understand why we talk about benchmarks, what we mean by a benchmark, and why they are important as a principle in forecasting. And then following that, we learn how to specify and estimate models or fitting models using Fable, and then how to produce forecasts. I will show you also how to visualize your forecast and also the fitted curve that we have. I will briefly talk about what you mean by fitted values and also talk about residuals, but I will come back to this on day 5, where we talk about how good a model is, and a part of it is also to look at residuals. All right, let's start talking about what we mean by forecasting. So if you remember, the first day we started talking about a workflow that we need to go through when it comes to forecasting. Well, we didn't really talk about the first 2 steps, but they are fundamental when it comes to forecasting. So most of the time, what happens is we get the data, and then we just think, there is a variable I need to forecast, and start, producing some forecast and plots and so on. But as a principle, we should always start with a decision and understand why we do the forecast in the first place, or how that forecast is going to be used. So you can imagine that you have the most accurate forecast possible. So if you have that, how that is going to be used, who is going to use it, and in what way. And when we understand that, and I call it a decision here, when we understand the decision, and remember, when we have to make decisions, there are multiple inputs to these decisions. One of them could be forecast, but sometimes you may also produce multiple forecasts that fits into the decision-making process that you have. So once we understand this decision, or several decisions, for each one, we have to come and understand the forecasting requirements. So what I mean by a forecast requirement, there are a couple of things that we need to be precise about. First of all, we need to determine what is the exact variable that I need to forecast. Often people confuse a decision with a forecast, but a decision is different from a forecast. So decision is something that we do in the light of the forecast. When we produce a forecast that tells us something about the future, and in the light of that, we make a decision. So it's quite different from it. So we have to understand what is the forecast variable. And following that, we have to understand also what is the temporal granularity of the forecast that we are interested in. Do you want to forecast for each hour in the future? Do you want to forecast for each day or each week or each month or each quarter or each year? So that's what we call it, the temporal granularity. And the third element that is also important, we call it the forecast horizon. So how far into the future you want to produce the forecast? I want to forecast, let's say, for next 24 hours. So in this case, my horizon would be 24. I want to forecast for 7 days ahead. So my forecast horizon would be 7 days. Or I want to forecast for next 12 months. In that case, my temporal granularity is months and my horizon is 12. So these are three important things that we need to determine. There are some more things that we can talk about here, but I leave this to you. While this is really important, but it's not the part of what we want to cover here. But if you have any question about this, happy to answer. But I again recommend you to start with a decision, not actually jumping into the data analysis and forecast. Make sure you understand the decision-making process well, and then that dictates the rest of the forecasting process. So once we have done the first step and second step, well, we go look at the data preparation. This is what we have done using Tissable. So you learn a lot of things, and we keep actually introducing more things as we go through the days and sessions. But the most important part of this is Tissable, but also the functions we have in dplyr from tidyverse. So you can do a lot of things here. And then once you have the data that is ready, you can go and visualize them. So here we also learned some time series graph. And today we learn how to choose and train models. We also learn how to produce forecasts. So we'll cover step 6 and step 7. On day 5, we will cover how to evaluate the quality of the forecast. So in a way, we also skipped step 3. This is also really fundamental. But we assume, based on what we cover in the training, we assume that we have the data and information for whatever forecast you want to produce, and then we take it, from there. But in real world, this is also a step that requires lots of attention. So where is this data? How it is the quality of that data? Is it publicly available? Can you bring multiple data sets together to do something interesting rather than just relying on one single data set? So these are also things that you need to consider. Okay. So if I put, these steps together, so I have to prepare my data. We use mainly Testable here, and then visualize data with time series graphic, choosing and fitting models, produce the forecast, and evaluate the quality. So that is what we cover now in this training, and we have covered already the first and the second one, and today we cover the fourth and the fifth one. So now, before going through this and learn how we do it in R, let us think about what a forecast is again. So on day 1, we discussed about a definition of forecast, and we typically look at the forecast as estimation of a future based on the information we have at the time we generate the forecast. Now, often when people talk about the forecast, they actually referring to a single estimation of the single point estimation of the future, a single number. Let's say if you want to forecast the number of malaria cases in Kenya, so they say, well, maybe in December 2025, we're going to have 200 cases. In January 2026, sorry, December 2025, 200 cases, January 2026, 400 cases, and so on. So you see the estimation or the forecast we provide is a single number, right? But the reality is the future is uncertain. So there are a lot of things that may affect the future. So if we produce a forecast as a single number, we don't really acknowledge the uncertainty in the future. So we need the definition of the forecast that help us to tell people Well, the forecast is uncertain, and this is basically how I can tell you about the uncertainty of that variable that I'm forecasting in the future. So in a way, we can define a forecast um, as a random variable as well. And it is what we do is to estimate the probability distribution of that variable that we want to observe in the future. So rather than relying on as a single number, we try to capture the possible outcomes that we may have about that variable in the future. And of course, they may have different likelihoods. And if you are a statistician, maybe this is something you understand quickly, but if not, don't worry. Now we go through it a bit more slowly. So now let's look at one example. So what I mean by this. This is similar to the tourism data set that you have looked at previously with Mitch when it comes to time series graphic. So in this case, in x-axis, I have months, and then in y-axis, I have thousands of visitors. So what we can do is we can fit a model into this historical time series and simulate from it and produce one possible future. So what I can do is I can keep doing this, fitting a model, simulate, produce another possible future. And I keep doing this, and I can produce 10 different possible future and even 1,000 different possible futures. This is something we call also trajectory forecasts. So we have actually different paths. Here we have around 1,000 paths. So I can put all these paths together, and it gives me an area where the future outcome might lay down somewhere, but I don't know exactly where. So one thing that I can do as well is for each period that I forecast in the future, I can go and take, if I produce 1,000 possible future, I can take the average of them. And this average for each month in this case gives me a point. If I link those points together using a line, I will get this blue line. And this is what we call the point forecast. If I zoom in a little bit, so not only I can see the point forecast, but also I can generate also what we call the prediction intervals. So this is an interval with a probability that the future outcome can also lie down there. So we can have any prediction interval we want, 50%, 80%, or 95%. And as the prediction interval becomes, or the probability increases, also, of course, the interval increases as well. I have to just emphasize on one thing here. Sometimes people refer to prediction interval as confidence interval. Just we need to make sure that we understand that these are two different things. So when we refer to prediction intervals, we are distinguishing it from a confidence interval, because a confidence interval is often about is referring to estimation of the parameters in a model, but the prediction interval is about the future. In a way, prediction interval accounts for two types of errors, but the confidence interval is just one. So in prediction interval, we have what we call both reducible error and irreducible error. An irreducible error is something we can't do anything about because it's completely random and we cannot predict, or we cannot actually reduce that error in a way. All right, so far, what we just did is just to show you what alternative we have when it comes to defining a forecast, rather than just relying on a single number. So we can produce different paths or different trajectories, thousands of them, even a million of them, if you like. And then from there, I can have an understanding of possible outcomes I may have in the future. So I have show you how we do it with trajectories, but I could also go and create a histogram, so let's say density plots or possible periods in the future. So in this case is I created histograms like this, and I rotated it 90 degrees just to look like this, to match basically the periods. And this histogram has a shape. But I can also show you a density just to understand better. So this is an example of normal distribution, but we could, in theory, get basically a distribution or probability distribution um, for anything that you want, like Poisson, negative binomial, or any other distributions. So let us first understand what a probability distribution or probabilistic forecast or forecast distribution tells us. So whenever you see something like that, which is similar again to here I have the histogram, but here I have a density, and I rotated it to understand it a little bit better. So what I have in x-axis, I have possible outcomes in the future related to variable I'm forecasting. In this case, is demand. So in x-axis, I have possible outcomes, and in y-axis, I have the likelihood of them. And of course, I have, the center of this distribution with mean, median, or mode, and I go to the tails as well. The likelihood decreases as I go to the tails. So it means there is less probability of having the demand, let's say, less than 450 in this example, or more than 540. So what is important for us to understand is once we have a distribution, you can take different moments of this distribution and extract a lot of information from the distribution, including point forecast, prediction intervals, or any quantiles that you are interested in. So as you can see, when we have the forecast distribution, we have all the information that we can get about the future. And you can get this and communicate to whoever is interested in this forecast based on the information that they need. You can communicate the whole distribution, but sometimes you may just want to communicate, let's say, one particular quantile, or just a prediction interval, or maybe only point forecast. But what we need to remember is we have all this information now. This is really rich, and it acknowledges uncertainty in the future as well. And this is what we need ideally to make better decisions when it comes to the future. Some notations may be more useful for the book if you go through the book later. So we have a variable or things that we want to forecast. We refer to this as yt plus h. So remember here, h is the forecast horizon. So how many periods into the future I want to forecast. And then we have y1 to yt is basically our historical time series data from period 1 to period t, which is the last period. And after that, I have the future, which is, let's say, t plus 1, one step ahead, t plus 2, two step ahead, and t until t plus h, which is h step ahead. And then from here, I can get a conditional distribution for the forecast. So I want to forecast for period t plus h given or condition on t. So which means I have the information from the first period until the last period of the time series data. So once I have the distribution, I can get the expected value of that distribution, which gives me the point forecast. And I can also get the variance from that. But as I said, you can extract any other information like quantiles or prediction interval using that. And I will show you all of this, how we do it using Fable. Okay, so this is just again, in a way, redefining what we mean by a forecast. So remember, most of the time people see forecast as a single number, but we want now to change that definition. We say that the forecast is not a single number only, because a single number doesn't account for uncertainty. What we see as a forecast is typically a distribution. And from that distribution, we can extract any information that you want. So from now on, whenever it comes to a forecast, remember, this is what we should know as a forecast. Now, let me show you this example. This is an example from real data with the time series that I showed you before. So here I have the historical data. I fit a model into this, and then I produce a forecast. So here I have the forecast with intervals and the blue line, the point forecast, and I also put the actual numbers as well. And as you can see, it seems like the model is doing a really good job. Why? Because the time series that you can see here has some regularities. So yesterday we talked about, or day before we talked about the seasonality with the consistent period of time. So you see those repetitions, they have a consistent length. And it seems like this is the case here. So until, let's say this February, it seems like the model is doing a pretty good job, but something happens here. Anyone, you can maybe put it in the chat, and I don't have access to the chat, but Mitch, maybe if you are there, you can have a look. And so I just want to know if you can guess what happened here around this period.
Okay, one person suggests COVID, two.
Right? Okay. Yeah.
There was a decrease, COVID-19. Very good.
Absolutely great. So yeah, absolutely. So basically, what happened here, as we know, COVID happened, and because this time series is about travel, so it's about visitors in Australia. Well, COVID happened. We had lockdowns, travel bans, and then suddenly the number of people visiting from like thousands of people dropped to almost zero. Okay, now we understand that. But let's understand what the model is doing here. Well, the model is like the forecasting that we have produced is continues to do the same thing, right? Well, one reason is because the model doesn't know about the COVID. And this is something interesting. So that brings up an interesting question. What can we forecast? So the model was doing a good job. COVID happened. The model is again doing similar things, but the reality is different. Actually, this is an example of a forecast failure. So in this case, the forecast model failed. So the question that we are asking here, what can we forecast? So we are interested in understanding if there are criteria that we need to think about when it comes to a variable that you want to forecast. Well, there are a lot of things that we can forecast. The question is how good those forecasts could be. If you think about financial market, there are many things that we can forecast. I don't know, maybe a closing price of Google or Meta index could be one variable that you want to forecast. The currency exchange of pound versus US dollar, again, is interesting if you want to forecast that. The consumption of a particular drug in a drugstore, or for example, in your exercise and apply, you have vaccines for different health center, different county, sub-county. Can we forecast that accurately? We can also forecast load. One thing that we see almost every day is the weather forecast. And if you do forecasting in general, and if you tell people, yeah, I do forecasting, probably the first question I ask you is about forecasting weather. And then my wife blames me a lot every time if the weather forecast is not accurate. So he blames me for that because somehow I'm just interested in forecast. The time of sunset or sunrise, again, is something that we can forecast. And a lot of astronomical events like comet, these are the sort of thing that we can forecast. So here is a challenge for you. So we put 8 different statements in terms of different variables that you want to forecast. So I want you to read them, think about them, and then I will give you now a link where you can rank them from the easiest to the most difficult. So here I have daily electricity in 3 days. So remember, I have a variable And in some of them, you have also a horizon. So is it for the next 3 days, not for next 365 days? Or this one is next year, or this one is in 6 months. So maybe you can think about that as well at the same time. So please think about this. And based on your knowledge and experience, rank from 8 to 1, the easiest to the most difficult one. And let me share this link here. So I'll put it in the chat. Again, is a Mentimeter
Yeah,
tool. I would really appreciate it if you join in or just mute yourself. Thank you. So I put the link in the chat. If you don't mind, please click on this. So you'll see all these options. And then you have to click on them, right? So the easiest, the first click, and then the second easy, the second, and so on. So you just click them based on that. I'll show you the result in a minute to see whether we have an agreement on which one is the easiest one, which one is the most difficult one. So my guess is we might agree on some of them and disagree, but again, that is fine, because things might also be different depending on how we look at them. So I will leave you like 1-2 minutes if you can do this exercise. I can see already 34 people that are busy there. This could also be based on your own experience. If you have done or being involved in any forecasting task, this could be also helpful. So I don't blame you if you don't know some of this. Like, I don't know, the timing of the next Halley's Comet appearance is fine. So just keep maybe doing this. I'll bring in this here in a minute. Okay. I think you should be able to see the screen. So if you can keep voting, we'll see how this maybe changes. So what is interesting that we see time of sunrise and time of next Halley's Comet. It seems like most of you believe that these are the most difficult ones to forecast. Which is interesting. Again, this could be just because maybe you're not aware of what is happening there. Completely fine. All right, so it seems like things doesn't change much. So most of you believe that maximum temperature tomorrow is the easiest, followed by daily electricity demand, and then Google price, and then total sales, Google stock price in 6 months, exchange rate. I think I really like this 1 to 6. It seems like it completely aligns with the way I think as well. But then suddenly this 6 and 7 change things. Because for me, this 6 and 7 actually could be somewhere in the top of this list, right? Not maybe in the bottom. I think that's the only difference. So actually, it's quite easy to predict the time of sunrise. Um, and also, most of the astronomical events, we can predict them precisely, comparing to other things. And again, this is quite different from the sort of forecast we do. Um, and there are reasons why it's not difficult to forecast them, it's easy. So apart from this too, I think I agree with the sort of thing that you put here. So temperature for tomorrow, daily electricity, Google stock price. Again, the order could be maybe different slightly, I would say. And it depends on some other factors as well. But then I will definitely put exchange rate and Google stock price in 6 months in the bottom of this, because these are not really easy to forecast. Now, my next question then is, because I think most of you answered correctly, and this is aligned with what I think as well. So we can have a follow-up question on how to measure what is easy or what is difficult, or what makes a time series easy or difficult to forecast. So in general, something that you want to predict into the future, how do you determine if it is easy or difficult to forecast? What are the criteria that you think about? By the way, Mitch showed you yesterday how you can extract features of time series. There is a feature that you can extract from that package or functions from that package called entropy. And entropy could be also one of the features that you could actually use um, to tell you about forecastability. So entropy is a feature that tells you about the ratio um, of systematic information to noise. And that's an indication of forecastability, how easy or difficult it is to forecast a time series. So now my question is, can you please, based on your thoughts and experience and the poll that just we had, can you list criteria that you think can help us to understand whether a variable is easy or difficult to forecast? Can we get good forecast for some, but maybe not for others? And here, I generally, when I say good forecast, I'm talking about an accurate forecast. So when we use term good in forecasting, good could mean many things, but here I just refer to accuracy, how accurate the forecast is. So if you don't mind, please put your responses in the chat. I'll probably have a look here as well. Okay, perfect. So I can see timing. I'm not sure what timing could mean here, but natural phenomena, availability of past data. Yeah, absolutely. Horizon, of course, how far into the future you look at, it affects also how good the forecast could be. Again, you can see historical data. Yeah, so again, about the horizon, so shorter terms to longer terms, typically easier. And then another criteria is about, again, historical data. Of course, good quality is important. Yeah, this is also a very good point. If you are dealing with a variable and that variable in general is stable, it means that there is less randomness around it, is also easier to forecast. So I suppose when you say consistent data, you may also mean there's less randomness around it, more pattern. So again, I see a lot of past data, great. Yeah, again, great, stable patterns. So we have the patterns that we see in the past, and we expect those patterns to be observed into the future. And again, you refer to a few unexpected fluctuations, absolutely. So you talking about randomness here as well. And then here there is another interesting thing about outliers. So again, outliers could be a different thing, but I suppose here you mean sometimes you observe values that are extremely low or extremely high. I agree completely. So they affect the quality of the forecast, and we need to think about how to deal with them. Again, forecast horizon. I'm just trying to see whether there are other things that we haven't covered so far. So again, there are a lot of points about data quality. This is correct. Yeah, so again, thank you, Amal. This is also a very good point. So this is something that we haven't observed before. So factors that affect the variable that you want to forecast. Absolutely. So how do you really understand what factors affect our forecast? So thank you so much. These are really great and relevant points. And again, these are not a comprehensive list, but I put some here that agree with what you have also discussed. So typically, something is easier to forecast if we have a good understanding of factors that contribute to it. So let's say if we talk about load forecasting, we may have a time series of historical data. Maybe we have, uh, temperature that affects that. And then that temperature could tell us more about, let's say, um, load consumption. That could be a good understanding. Or let's say if I'm forecasting um, number of patient admission in a hospital, maybe if there are festivals or I don't know, football matches in my city, and every time that happens, I see more people in emergency departments. Again, it could help me to understand what affects my variable of interest. So this factors is very important. And the second is about data availability. So the forecast variable you are interested in also depends on how much data you have. Again, the question of how much data is also interesting because there is no optimal lens. So forecasting methods, they require a minimum lens, but there is no maximum lens. Typically in time series, we tend to say more data in terms of historical time series is better, especially if we care about the probabilistic forecast. But having more data in terms of history help us also to produce more reliable forecasts. Now, there is another important factor that wasn't mentioned in the chat, which is very important as well. So if you are dealing with a variable, and if you forecast that variable, and the forecast later affects people's behavior, and then people behavior changes, and that will affect basically the final outcome. In a way, the forecast it affects itself. This is the case in many examples where we are dealing with people behavior. COVID is one example. So you forecast the number of cases. If they increase, the forecast says, well, if you don't do anything, it will increase. There would be a lockdown. And then following that, people behavior changes. And then, of course, the numbers would be different now compared to what you forecasted initially. When it comes to currency exchanges is another example that we see often here. So this is also important to remember. Most of you mentioned also about randomness. So if you are dealing with a variable where naturally you have less variation or randomness around it, it means it is possible to get also reliable, good forecast there. So the last point that I have here is about an assumption that we typically have in time series forecasting, and that is we assume that future somehow is similar to the past. Here, it doesn't mean that the future will be exactly like the past or repeats. Here, we're talking about the same sort of systematic information we observe in the past. We expect to observe them in the future as well. But you saw in the case of COVID-19 and the graph I showed you, that was not the same, right? So when COVID happened, the future was different from the past. So the assumption was not true anymore. So that's why we keep producing the same forecast, but the forecast failed and it was different from the reality. So these are some points that you need to think about when it comes to forecastability. So let me also um, just share one chapter that we have actually in our book here that is exactly about this, and you can read more about that. So we have a chapter called Why Does Forecasting Fail? And this covers some of the points that I have discussed here. And you have maybe more time to look at this in a bit more detail later. All right. So now we have an understanding of what a forecast is, and we also hopefully develop an understanding of there are factors that affect the forecastability. So before going into the modeling part, think about these two things before going into the data analysis and the modeling, because that helps us to at least set expectations. And whether there is a possibility that we do some good modeling and we get forecasts that are helpful when it comes to the future. So in many cases, the forecast exercise could be really helpful because it can help you, but there might be also cases where none of this criteria is there and it is really difficult to produce a forecast. Now, the next thing that I'm going to introduce is um, basically start introducing forecasting methods or models. So today we just talk about some simple models, and from this afternoon and tomorrow we introduce more models that you can integrate into the workflow. So I will start with some models that I call them benchmark. So before going into this, can you tell me what a benchmark is in forecasting? And why do we care about having a benchmark? So I want to emphasize that having a benchmark in any forecasting that you do is fundamental. So basically, I always consider this as one of the best practices in forecasting. Maybe you can put your answers in the chat. So what consists of a benchmark and why it is important in forecasting? So I cannot see anything in the chat. Maybe I can wait a little bit more. So my question is, what is a benchmark method and why it is important? Yeah, so all right, so good answers. So there is one about to compare complex models. So this is answering the why, maybe for best performance model evaluation. Yeah, absolutely. Again, is about model evaluation. Establish a baseline for comparison. Absolutely great. To make comparison, absolutely. So this actually, you are answering the why. Why do we need a benchmark? So what is a benchmark? what do you consider as a benchmark method? Okay, so I can see one for evaluating new models against established ones. So the term established ones is interesting here. So again, what we mean by established ones could be interesting. A reference point, yeah. Again, a classical method, depending on what you refer to classical, but yeah, so these are great answers. So what is a benchmark? A benchmark, so again, some of you mentioned established. It depends on the area. In some areas, you may have a method that is known as the established method. So everyone refers to this method. For example, in the case of vaccines, again, for those of you who are familiar, you know that UNICEF or Gavi or WHO, they have their own method of forecasting demands at the national level and yearly, which is a demographic forecasting method, right? So now, if you want to come and generate new forecast based on a method that you have developed yourself, well, you have to show people that your method somehow is better than the method developed by Gavi or by WHO or UNICEF. Otherwise, what is the value? Because the method they have developed is really simple and it seems like it works as well. So sometimes benchmark could be a reference point or an established method that everybody is using. So if you're an organization, maybe they have already a method. So if you produce or introduce a new method, you have to always compare against that. And if the method you propose doesn't improve, so what is the value? You cannot really sell it to people. So that is one thing. The second thing is a benchmark sometimes could be the simplest method that you can find. Is a method that everybody understands, regardless of, if it is established or not, or it is accepted in the industry or not. So we can have either of this or both of them if you like. But this is fundamental. Whenever you do forecasting, you have to make sure that you have a benchmark. So here we have some simple methods. I just skipped this because I wanted to ask you, how do you forecast this? But let me introduce three really simple forecasting methods. The first one, we call it total average. Basically, what we do here is we have all the historical data. We add all observation in all periods and divide by total number of observation and will give us the average. And this is actually the line that you see here. So we get an estimation for every observation. Based on that, we call this a fitted value, and then we produce the same thing for the future as well. So if you forecast using future, you'll see this straight line. And of course, it's just a total average. It doesn't account for any trend, any seasonality, anything, right? So the future values are equal to the total mean of historical data. The second simple method, we call it naive. What naive does is, if I want to forecast for tomorrow, I look at the value of today. If I want to forecast sales of tomorrow or the consumption of the product for tomorrow, I want to look at what I had yesterday and use it as estimation for tomorrow. And actually for day after tomorrow, for 3 steps ahead, 4 steps ahead, each step ahead. Again, here it's constant. It doesn't account for any uncertainty. It doesn't have any trend and seasonality and so on. The third approach, we call it seasonal naive. This is similar to naive, but instead of looking at the previous period, I look at the previous season. So what I mean by that? Well, here we have M. Basically, M here refers to the seasonal period. Again, the equation looks a bit complex. It is not really. So seasonal naive, it goes and says, first of all, understand what is the seasonal period. Well, seasonal period depends on the length of seasonality, and that depends on temporal granularity that you have. If you have quarterly data, M is 4. If you have monthly data, M is 12. Okay, let's look at the M12. And assuming I have the data up to November 2025, all right? So for the past 10 years, I have the data up to now. Now, I want to forecast for December 2025, January 2026, and so on. So if I use seasonal naive, what I do? Well, to forecast for December 2025, I go back M period. In this case, is 12 period. So I look at what I had in December 2024. That's the forecast for December 2025. If I want to forecast for January 2026, I go and look at the value I had for January 2025. So if you do that, somehow you can capture the variations basically that you observe in most recent observation from the time series. And then another, like the fourth approach that we introduce here as a simple method is called drift. So what we do in drift is we actually capture the changes because these are subsequent observation. Again, remember we have period 1 to period t in this case. So we calculate the difference between consecutive periods. So we cannot have the t equal to 1 because there is nothing before it. So we start from 2 and we calculate those changes and we divide by total number of periods and multiply by h plus the last observation. And if you do some simple mathematical I'm simplifying using some algebra, actually we get this equation, and this means to forecast using drift for h step ahead, I take the last observation and then I add this to the difference between the first and last observation divided by the total number of observations and multiply by h. So this is like extrapolating line between the first and last observation. Basically, you will get something like this. So this is the last observation here. This is the first observation. So you link them together and then extrapolate, and that will be the forecast for the future. So again, I think the idea of this method is straightforward, is simple, but R will actually does everything for us, so we don't need to be worried too much about it. So now let's focus on step 4 and 5 here. These are really important because whatever we do later relies on this. So I recommend you to take some notes if you like in terms of what we talk about here. And then we repeat most of this in the afternoon and tomorrow and on day 5 as well. So hopefully by repeating them, they will, stay in your mind and you can actually use them without even thinking about them at some point. So now let's learn that how we specify and estimate models in Fable. So now we introduce some simple benchmarks, and I'm going to show how we do it with this. But remember, this is the same for any other models that we do later. So the first thing we need to know is how we specify model in Fable. So in Fable, which is a package under FPP3, because you have installed maybe FPP3, so one of the packages inside it is called Fable. We do forecasting using Fable package. So Fable supports a formula-based. What I mean by this is in R, generally when we express the formula, we have a right-hand side, a left-hand side, sorry, a tilde, and then right-hand side. So what is in the left-hand side is basically the variable that you want to forecast. And then you may have a tilde or not, and then terms. What I mean by terms here is it could be different components of the time series like trend seasonality, or it could be external variables as well. So let's say temperature, population, if you want to forecast number of doses administered in vaccines, which is an example you have in apply exercise. So this is something you need to remember. So formulas, we have to provide formulas to Fable functions to be able to tell the function, this is what I want to forecast, and I have these terms. Sometimes you don't need to provide the terms because the function by default has some terms and you don't need to specify them. This is mainly helpful when you have external variables, but also you do it with regression as well. So Mitch will show you how to do this in the next session. um, with regression. So that's one thing you need to remember. Another thing that you need to remember is, in general, you know that R is case sensitive, but what you need to remember, every single forecasting method in Fable has a name, and the name is in capital letters. So for instance, if you want to use seasonal naive, the name of the function for seasonal naive is snaive, and it is in capital letters. So this is, again, something that you need to remember. So now we start by understanding what is the name or a function for each forecasting method. So we have to learn them. And once we learn them, we have to learn how I train my model and the data. So this is basically a template for how we do it. So I have my data. Remember, this data needs to be in a testable format. All right, so that's something we have done in the past. I pass that to a function called model. And inside that function, I choose a name equal. This is basically something you type yourself. So you choose a name, you type a name, whatever you want, equal, and then here is the name of the first model. And then inside the parentheses, you provide the arguments for that model. Most of the time, the argument is response, is the name of the column in your testable data that you want to forecast. And the terms, again, could be maybe different external variables or some other specific functions that we have in Fable. So if you have multiple models, you just put a comma and then add the list of models like what you see here. All right. So I will show you basically in a minute, maybe with a live demo. So once you have a data set in testable and you pass it to the model function with the list of specific models, and if you run this code, you will get something that we call it a model table or Mabel. Okay, so we need to understand what is in a model table. So in model tables, we have columns. But look what we have here. It's exactly these names, right? And what is inside the name is actually what I have here. So I fit a model into a response variable. So once I run this, I get a model table, and each column is about one method, one forecasting method. So that's one thing. And then I have rows as well. So for this one, I have only one row. Why? Because I have only one time series. If I had many time series, you will see many, many rows. You will see some examples later, for instance, with tourism data, because we have many time series, you can see many rows. So this is the first thing that you need to remember in terms of the output. So first, we have to learn about the name of the functions. So snaive is for seasonal naive, naive is for naive method. So random walk with this term drift, it tells us that I'm using basically the drift method, and then mean is about total average. So this is the name for those functions. That's the first thing we need to learn, name of the functions. Once I have that, I need to know that I need to use a model function, and inside that provide the list. And when I run that, basically I fit these models into my data. So inside each of these objects, I have different information and I can extract them. How? Using these functions. Report, tidy, glance, and more functions that we introduce later as well, like components or augment and so on. So again, you can take some notes when it comes to this, especially these are helpful when we do time series regression or we do exponential smoothing or ARIMA. So far, I just specify the models and fitted or estimate parameters. And of course, I can go and check also how good these estimations are. This is something I leave it for day 5. All right. Now let's see how we produce forecasts. producing forecast is extremely easy. We actually need just to pass what we had so far with the model table into a function called forecast. And inside the parenthesis, I provide the horizon. So the horizon I provide is h equal, and this could be either a number, let's say 4 or 5 or 12. And the function automatically knows about the index of your tessable, and it knows that if you say 12, because your index is monthly, is a temporal granularity is months, you're talking about 12 months. So it knows that. Or you can also provide the natural language. So one important thing that you will see in the apply exercise for vaccines is if you have external variables, depending on how you use them, you may need also to provide the future values of some of your predictors, and you do it inside the forecast variable. So you have your model table, you pass it to the forecast function. Inside the parentheses, you provide the forecast horizon, and that gives you a forecast table or fable. So here again, number of rows, number of columns. Here it tells you about the index. Here it tells you how many models you have. We have 4 models. And then the table itself. So that model contains the name of all the models, quarter. This is about the period that you want to forecast into the future. So this column here, again, is the name that we want to forecast. And it under this is as a data type of dist. And remember, here I get a distribution. So most of the time in Fable, the distribution that we forecast is a normal distribution with a mean and the variance. And that mean here, it means just the mean of this distribution. That's why you see that these numbers are the same. All right. So we get not only the distribution, but also the mean, and we can extract any other information. I could also go and visualize basically things here. So I could visualize the forecast that I produce, and I could also plot the historical data. Okay, so we discussed about the forecast distribution. And then I want to show you basically an example now, because this is something I think I have covered. I will probably come back to this if I have time. But I just want to show you that how we produce the probabilistic forecast. For the 4 methods that we produce so far, and specify methods, fitting, and then producing the forecast, we can have basically this equation for them. So assuming that we have residuals after fitting a model, they look like a normal distribution, and they are uncorrelated, and the variance of those residuals are constant, we can have these equations to get the forecast for t plus h condition of t. It means I have the data from period 1 to period t. So this follows a normal distribution with this mean and this variance. So this is for method mean. So for naive, we could have something similar with normal distribution. This is the mean. And this time, the variance is basically the variance of residual multiplied by h. So remember, this one doesn't depend on h. So it means the uncertainty is constant over time when it comes to mean. But for naive, it is increasing because you multiply that by h. And actually for seasonal naive and drift, the variance is also depends on h. Because here we have a k, and k basically is the integer part of h minus 1 divided by m. So the variance of this also increase over time. The only one that is constant is this one. So if you look at these equations, and especially if we are just interested in one step ahead, and we have a lot of historical data, these all give the same approximate forecast variance of sigma squared. So basically all this disappears. It will become 1, 1, 1, and then 1. And I will just get sigma had a square, so the variance would be same across all of this. So we don't need to be worried about this because all this is integrated into Fable, but it is just good to know that how Fable is producing these distributions. So one more thing. Remember, most of the time in Fable, the forecasts are produced using normal distribution. So now, if the condition of normality is not valid for the residuals, you may want to produce a forecast using a different method. So in Fable, you can also produce a forecast using a method called bootstrapping. So bootstrapping is a sampling technique. What you do here simply is you fit the data into historical data, you produce one step ahead forecast, and you go and sample with replacement from the residuals that you had in the past. And that will produce one possible future. Now you take that as a next observation, and you go and sample again from the past residuals, you add it to that, and you keep repeating this many, many times, and you produce basically those 1,000 trajectories or passes that I showed you. So one way that we can produce the probabilistic forecast using Fable is with normal distribution. It works actually in many cases, but if you believe that the normality of residuals is not valid, you can also do using bootstrapping, which is a non-parametric approach for probabilistic forecasting. So you can do that. I think now I can show you maybe this one with an example. And then I can extract, any information with Hilo when it comes to prediction intervals. And I can also extract the quantiles from that as well. Okay, so let me now move on to do basically, I don't know how much time I have. Maybe I have about 20 minutes, I would say. So let me do some code here just to show you how this actually works in practice. And what I do here, I will share it with you at the end, but you could also try to see if you can replicate this with your own data. So here, first, I will start with providing a list of libraries that I'm using here. So I start with, yeah.
Sorry, you just got a couple of minutes and then it's a break time, but you're welcome to go into the break time if you like.
Oh, okay. Sorry, I thought, so the break time is now or is in 15 minutes?
It's in 1 minute, yes.
Okay, sure. So can I maybe continue this after the break?
Yes, of course.
Yeah, okay. So let's maybe have a break and then I will probably do this live coding in 15 minutes. I think 15 minutes should be fine. And then I think Mitch will continue with that later. All right.
Great. If you've got any questions during the break, feel free to ask them and we'll do our best to answer them.
So there is a question whether the forecast and prediction is the same. There's a good question, actually. It comes up all the time. So some people, they don't really distinguish between a prediction and a forecast. I think in the forecasting community, we tend to distinguish a forecast from, so predict from forecast. So I think when we talk about forecast, what is important is there is always an element of time. That is one thing. But when we do prediction, sometimes you may deal with things, you predict things, but it's not about time. An example is, you want maybe you have a data set about houses. Each house has different features or different variable, and then there is a price for the house, right? So this is the historical data. Now you get a new house with different features, and you want to predict the price of the house. So in this case, there is no basically time element in it. And this is something we call the prediction. Another difference, the difference between a predict and future and forecast is in forecast, we typically talk about the multiple periods ahead into the future. So like 6 months ahead, 12 months ahead. So this is also not the case in prediction. So I think these are two things that comes to my mind, how we distinguish predict from forecast.
The other interesting thing for the difference between prediction and forecasting for me is when you're doing a prediction from, say, a regression, a cross-sectional model, you want to be careful not to extrapolate outside of the data where you've got support. So you're usually making predictions about things similar to stuff that you've already seen before. But forecasting is always extrapolating. We're always going into the future for data in time that we've never seen before. And that's where a lot of these assumptions come in, where we assume that the future is going to behave similarly to the past. Otherwise, our extrapolation will be inaccurate.
Yeah, and also projection. Yeah, again, these are a bit like vague terms people use. Projection. Sometimes it's even I heard terms like trend analysis and this sort of thing. Again, I suppose they mean forecast. So projection, trend analysis. Most of the time, people use this sort of terms, but they mean really forecast. So another question: how do we choose between normal and bootstrap? So as I said, so there are some assumptions that comes with the normal distribution one. So the assumption is we assume the residuals are normally distributed. So if you look at, and this is something we do on day 5, we look at the distribution of the residuals. And so if the residuals are not normally distributed, maybe the assumption is not actually valid to use. And that's maybe one reason. So you go and use bootstrapping. For some reason, I was thinking we have 1 hour and a half and then a 15 minutes break and then 1 hour and a half. Maybe I don't know why I was thinking like that. Okay, so maybe you can have a coffee, tea, or, you know, just a glass of water if you like. And I will be also back in 5 minutes if you have any other question. And then I will do a live demo of maybe 10 minutes, not to take a lot of Mitch time as well.
If you don't want to eat or drink, it's a good idea to get up and stretch. Important not to stay seated for too long.
Mish, I think the break was at 8:30, if I'm not wrong. But anyway, it doesn't matter now.
Looking at the website, I see.
Is
Uh,
half past. That was what I was planning, but anyway,
oh,
I'll just
I'm very sorry. I was looking at the wrong. I was
don't
looking at
know.
the second session finishing time.
No, I was because I put my alarm, and then I thought, I put it for 1 hour and 20 minutes just to tell me that how much, and I just realized and I checked it. No worries. So anyway, is
Well,
we have
we're
15
right on.
minutes?
You got plenty of time for your demo then. Sorry about that.
No problem. It's fine.
So we'll start in about 6 minutes.
So I will start in about 2 minutes. Can you see my screen, everyone? Okay. Okay, thanks. So before I show you some demonstration in R, let me tell you actually what I'm planning to do. Assuming we have like a time series and we start plotting it, so we know how we plot let's say a time series data, assuming this is my historical data. This is now, I'm talking about real time, and this is my future. Okay, so this is the future after the red line, and this is the past. So what we do in real time? Well, typically, let's say I have a forecasting method. What I go and well, another thing is remember these are different points. Each point is a period, and then I link them together and I create this line. Basically, that's what I mean. So I have the last one. If I want also to be a bit more precise, I will create periods here. And so on. Okay, so we have different periods. This is basically T, my last observation. This is period 1. And then this would be T plus 1, T plus 2, and then so on. So I need to forecast that. So typically what I do is I have a method, I specify the method, and then I pass it to the model function, and the model function will create estimations for this. For each period, it gives me estimation. And this is, well, let me, well, it's fine, I can use this color. And if I link them together, this will give me what we call the fitted line, right? And then after this, I can also produce the forecast for the future. And remember, I can produce the forecast as a distribution or as lines. So let's say here I have normal, so I will get basically something like this with a center, which is the point. For this period, maybe this period would be something like that with a center and so on. And I can do it for any h step ahead into the future. So this is basically what I'm going to show you now in R. So we're trying to create something like this. I could equally, instead of those distributions like that, I could actually have just trajectories. So again, one trajectory, another one, maybe another one, and so on. So I could create thousands of them as well. So this is another way. I will show you the first one, and if I have time, I do the second one. Otherwise, I will just give you the script, and Mitch will put it in the website, so we'll have access to it. I will just paste it in the chat as well later. So let me now go to basically my R session. All right, so I will share this code with you, don't worry. So for now, just pay attention to what I do. So first of all, I do load list of libraries that I'm using here. Some of them, they might be new to you. I don't think you have used maybe ggdist before. I mean, you can Google it, or you can actually looking at the VNet of this just to see what is that. So I'm using maybe functions from this and also functions from distributional. So this is another package that Mitch has been working on and developing. So if you want to work distributional, this. So if you work on, distributions and probability distribution, these are two packages that you definitely need. So I'm just loading these packages first. So if you haven't installed them, you make sure to install them before start doing things. And I know I work with, one of the data sets that we have worked with before, um, and that is aus production, which is the second one from Tissable. So you see, something like this code suggestion, and this is because I'm actually using uh, Copilot, GitHub Copilot, and that's why I see this kind of code suggestion. So this is another thing. Hopefully from next year, we will have some sessions also how to integrate AI tools for forecasting as well, but not this year. So I have my aus production. I pass it to another function using the pipe operator. So I type a pipe operator. And then because aus production has many, as you can remember, so I just select basically one of them just to be clear that which one I'm focusing on, and that would be maybe beer. All right, so remember, this is a testable now. I have an index and I have my variable that I'm interested in. Another thing that I actually do here, and now we are using a new function called filter index from testable. This is a function I will use a lot in day 5 as well. So if you want just to filter your index, because you want maybe to have the part of this data, you can also you do it using filter, but filter index is designed just to work with it. Actually, it already gives me something which is not too bad, but I just delete the rest of this. So filter index, I want maybe to have something from just not all of the data, but just a part of it. Again, this is only for this exercise. From, let's say, 2000 quarter one until 2009 quarter one. So if I do that, I just get basically a part of the data. You could also do it with whole data, but I just do it with this because it's easier to see the visualizations. So I pass this to a new name. I just name it Allspear. Okay. So this would be my testable data that I want to use for forecasting. So I want to forecast the beer variable. So how I do it, I take my testable, and then here I have to pass it to a function called model. Some reason it just goes and automatically do it. I'm not sure how to deactivate this, just not to see it. Um, so I have to provide a name. So this is basically my name as naive equal, and now a name of the function from Fable, which is in capital letters. And then the name of the variable from this testable that I want to forecast. So if I just run that, then I will basically get one column and one row. And this is because it's only one time series and one method. The good thing is you don't actually need to do much if you have many models or many time series. So for many time series, you don't absolutely need to do anything. It's just you're writing as it is. It will do the job for the whole time series. So another thing that actually I will do here, just again to show you some good visualizations later, is I do another filter index just to filter a part of my data and do the forecast for the rest of it. So this would be from 2000 and no, is actually I do it from the beginning. So in filter index, you can again look at this function. The help of this function, so it tells you how you can use it, but you can use a tilde like at the beginning, let's say. So that point means beginning or the end. And then at quotation marks, you can provide um, different periods that I have here. So I just do it because I want to focus on one part of my data for the fitting and then the rest of it to be for the forecast. All right, so I'm using just one method, but as I said, if you want to introduce more, put a comma, let's say add more methods, as simple as this. But I just use one for now because it's easier to show you the visualization. And I include an example in my script later that you can actually do more with that. So that's the first thing you have to do. And then I pass this to a name called fit. This is my model table or Mabel. Now, if I want to produce forecasts, I have to take my model table and I have to pass it to a function called forecast. So inside this, I have to provide an argument, which is h equal. So how many periods I want to forecast? Well, actually here, I did this filter index deliberately to have only 5 observations left for the future. So that's why I put this h equal to 5. I will talk about this filter index and how we do things automatically later in day 5. So here I just splitted the data a little bit um, to have 5 days, sorry, 5 quarters, because my data is quarterly. So 5 quarters to forecast, and then I want to visualize the forecast, but also match the actual data there so you can see things clearly. And then I just pass this to a name called FCST or forecast. So if I run this, and then I look at the object here, now I have basically my forecast table. So that model, because I have only one model, the quarter, how many periods ahead I want to forecast, 5, the distribution column, and then that mean, which is the point forecast. So, in 2 lines, I can produce already my forecast. Now, I want to visualize it. Actually, this one is a bit more involved than, what maybe do step by step. So basically, I actually have all my data here, my code here, and I show you what we do. So again, you need a bit of background in uh, data visualization using ggplot. If you are not familiar with ggplot, so it is actually easy to create visualizations with ggplot. So how we do it? Well, you type the function ggplot and you say which data I want to use to create a visualization. In this case, it's my forecast table. So I pass the data, my forecast table to data, and then I have an argument called mapping, and I have to provide which aesthetics I have. Well, aesthetics in ggplot means which column of my data, which is this table here, I should put in the display of a data visualization. And we have different aesthetics. The most common ones are X and Y, and also color, fill, shapes are different aesthetics. So here I want to say, take this uh, forecast table here, and then I want to visualize them, and I want to put X I want to put quarters in x-axis, and then I want to put distributions in y-axis. So if I just run this as it is, as you can see here, I get this blank thing, so that nothing happens. Now, there is a function from ggdist that I can use to actually visualize this column distribution. Well, this alpha, again, is not important. If you remove it, nothing happens here. So if I run this now, actually, I can visualize my forecast distributions. So I have 5 periods. This is the normal distribution for each one, for each period. And then I have the point forecast, which is median in this case. And I have, 2 lines here, this, if you can see them, these different prediction intervals. You can actually change all these prediction intervals. We have to look at the default is 80% and 95%, or 50% and 95%, I think. And if you want, you can change it. But one thing that I want to do now is I want to also add a bit of historical data to this, and then also add the fitted line. And actually, these 2 lines, this is actually what it does, right? So I will actually use 2 geoms, a geom line and geom point, just to see both points there. And then I will add this different lines. So nothing complicated here, is a bit of like ggplot thing here that I add, but I want to just show you how it looks like, and you will get this code as well. Um, the only thing I need actually to do here, that because here I'm using data called fitted, so I need to create this first, and I will show you what this is. It's something, again, I will show you more on day 5. So basically this fit and augment, it should be fit, not fair. Okay. It shows me the residuals and fitted values. So I can first pass my model table to augment to get this table, and now I'm interested in the fitted values. And I will talk about fitted value again later on day 5 a bit more. So if now I run this, I get actually what I wanted. So I have here the fitted value, the actual data in blue, and then the distributions, and also the point forecast as well, right? So this is, I will pass this code to you. It is good actually to have this kind of communicating visualization if you like later. You can also do similar things with the bootstrapping here. So what else you could do? You could actually take the forecast um, object or fable, and then you can type this function hilo. And if you just do it as it is, it gives you the prediction intervals by default 80% and 95%. And then this is the lower and this is the upper bound of the prediction intervals. So you can extract any prediction interval that you want from here. So you maybe saw that there is a option or argument called level here. And then you can provide, I don't, I just maybe 80, 95. Or let's change this to 50, 95. So if you do that, then you will get the prediction interval for any interval that you want. So you can extract prediction interval from basically this. So sometimes you might be interested in doing something like, unpacking basically this. So there is a function called unpack hilo. And if you want to unpack both prediction intervals, you have to come and do this 95%, 50% in this case, and then 95%. And then if I just run that, so now you get them separately in different columns. Sometimes you want to have that and extract it and maybe share it with other people. So you can also get them separately if you like. There is a relationship between actually prediction interval and quantiles, but you know what? If you want also to extract a quantile separately, you could also do this. So I just create new names. So mutate is a function from tidyverse, from dplyr. So I can create some quantile names. Let's say I want to extract quantile 10, quantile 50, and quantile 90. So what I can do is I can go and, what I'm thinking as I type, I think this is quite interesting what it does, this Copilot GitHub with auto-completion thing. So, but anyway, the function that I want to use here to extract quantiles is called quantile. And then this would be basically taking the distribution name, which is beer, and then a probability, which is about the quantile level 10%, 90%, 50%, and whatever. So I just get this copy basically here and then paste it here and one more time. So I change this to be 50 And so this should be actually 5, this should be 10, this should be, let's say, 90. So I changed this to be quantile 90 as well. So if you want to extract the different quantiles from the distribution, you can also do that. So this is the quantile 10, median, and quantile 90. So you see, this is basically what you can do, as simple as that. And now if you want to include more, it is similar to that. Well, it's already suggesting me new models that you will see tomorrow, ETS and ARIMA. So you can add any number of variables, and the rest of this would be the same. You wouldn't actually change much. But I will include the code later and will send it to you. So if you, let's say, have 3 methods here, this wouldn't work for 3 methods because it wouldn't be very good. So you may need to add a facet here later. So a facet wrap to have different facets or different plots, separate plots. Um, let's say for each model. On, so that would be probably one thing that I would do. So to summarize, this is actually what you do. First, you get your testable, you pass it to a model table, you provide the list of names. This is your choice. You write whatever you like because you use this name later. And following that, you provide the function name for the forecasting method. Inside parentheses, you provide what is the column name from the testable that you want to forecast. And then you can save it in a name. And then now to generate the forecast, you pass that model table name using a pipe operator to the forecast function. And inside, you have to provide the horizon. So if you want to create a visualization, again, nothing complicated. It's just a ggplot2 syntax. So you need to maybe learn a little bit of that. But before that, you need also to extract the fitted values because I need them to draw something here. And if you want to extract prediction interval or quantiles, you can follow, this code as well. So maybe I don't have time to show you the bootstrap, but I think for bootstrapping, or do I have time, Mitch? How much time? I don't have. I don't know how much.
The bootstrap's pretty important. I can adjust to the regression. We can skip a few sections of regression that's less important.
Okay, so basically, this is what we do with Fable when it comes to normal distribution. As I said, most of the time, it works perfectly. Especially if you don't have, the time series data with maybe zeros or low volume. If you are working with something that is high volume, and especially if you work with quarterly and monthly data, and even yearly maybe, um, I think this works perfectly most of the time. Now, if you want to use bootstrapping, um, this is also easy to do with Fable. Basically, we have our model table here, which is, we name it fit. We pass it to a new function called generate. Okay, so inside this function, you have to provide certain arguments. The first argument that I have to provide is the horizon, or yeah, how many periods in advance you want to produce a forecast for. So in this case, I will put 5. Now, the second argument that I have to provide is about how many possible futures or how many trajectories you want to forecast. I just provide 5 here, but you can change this to more because the problem is if it is more, it will take time. And then I have to provide another argument called bootstrap true. So I just delete this auto-completion code. And if I just run this, let's see what we get. What's this? Let me see. Maybe generate bootstrap true times. Is it times? I think that one. shouldn't be time. Am I doing something not right here? Okay.
You'll want to use forecast rather than generate when you set Bootstrap tree.
Oh, okay. So here I don't need bootstrap true, or let me, because I wanted to show the numbers
The
before
individual
going.
samples.
Yeah.
So for this one, if you
Uh,
is that working? It looks right. I'm not sure what the warning is, but it looks like it's working.
Sorry. So actually, it was working. Let me see. Oh yeah. So there is a warning, which I thought it's an error. So anyway, it's a warning. I don't know what is the warning, but anyway, that's fine. Let me just show you what we have actually here. Maybe it is better to see it here. So basically here I said times equal 5. So it will create automatically a column called .wrap. So it shows the number of possible futures that I want to generate. So here I want to have 5 passes. So it will change this wrap from 1 to 2 to 3 and to 4 and 5. And each time, because my horizon is 5, it generates actually 5 numbers or 5 possible futures for that. And it will put them in a column called .sim. So if you want to see those things individually, you could also do that. That's one way if you want to see. But there is also an option if you want to do it directly with the forecast function. So if you want to do it with forecast function, basically is, again, the fit that you have here. You pass it to the forecast function, and then you provide, this is quite annoying. You provide basically bootstrap. Bootstrap is just this one, maybe. Equal true. So if you do that, and then if I just run, so it takes a bit of time, but it will do it. Now, this time you don't see the individual replications or paths. Actually, it puts them all together, and by default, it will generate 5,000. So that's what I said. Here you can also change that to be different numbers, if you like. Rather than just 5, you could do the same. 5,000. So the rest of this, how we extract prediction intervals, how we extract quantiles, it doesn't actually change. Is similar to what we have with the fable or forecast table that we have here. So if you want to use Bootstrap and not the normal distribution assumption, just come to the forecast here and then go and change this to be bootstrap equal to true, because by default this is equal to false. So if you want to use bootstrapping, you have to just make it equal to true. I think the rest of it is basically similar to what we have done previously. Sorry, I saw the raise of hand. I don't know whether there was a question. Yeah.
I suspect that was a request to add code comments. So maybe after you're finished, Bahman, you can go through and add code comments, and we'll put that on the website.
Yeah, absolutely. I will do that. I will send this to Mish, and then he will add it to the website. But basically, this is what you need every time you produce a forecast. So you just go through these steps. And then from next session and then tomorrow, we just add more. We learn about, of course, more forecasting models. We add them here, but the process is the same. So, and remember, so far, we haven't, discussed about how good a model is. That's a topic we leave for day 5. So far, let's just learn how we specify models, how we estimate it, and then we look at also the Mabel a little bit in detail. I will do it tomorrow as well with exponential smoothing. And then how we produce the forecast and how we can visualize basically the forecast. So let's focus on this for my session. And then now with Mitch, you could also do a bit more on this. Is there any question or anything you want to highlight? All right. If there is no question for this, so maybe I'll pass it to Mitch then.
Okay, let's move on to the next session. So you've just learned about the basics of forecasting, and it's been a wonderful explanation by Bahman. I want to especially remind you of that forecasting workflow, because we're going to continue using that forecasting workflow, adding additional models that have different capabilities. Some can handle seasonality differently, such as multiplicative seasonal patterns. Others can handle cyclical patterns that we saw yesterday as well. The model that I'm going to introduce is one of the models that you might already be familiar with, but it has one special use for forecasting, which is using extra information. So on day one, we had a question about how can we incorporate multiple different variables, and we looked at how we can look at Victorian electricity demand and how that might relate to temperature. With the regression model, we can use those terms, such as temperature, as a predictor for what the future values of electricity demand will be, or ice cream sales. Any sort of information that we might have additionally can also be used for forecasting using regression models, which is fairly unique in the set of models that we'll introduce today. So I want to start with a bit of a show of hands. So you can use the react button on Zoom to raise your hand. I want you to raise your hand if you've used regression before. It doesn't have to be for time series if you use regression for any statistics. I imagine quite a lot of you have used regression in some cases before. Okay, fantastic. Thank you very much. Oh, I'm seeing lots and lots of thumbs up in addition to the hands up. So quite a lot of you are familiar with regression already. So hopefully this material will be a little bit familiar and you'll learn a few new tricks for how you can use regression models for doing time series analysis as well. So the purpose of regression models, as opposed to many other models that we work with today, such as machine learning models, they have this unique advantage where they help us explain and understand the relationships that exist in the data. We can interpret the coefficients of the model and learn more about the structure of the data. In addition to this, we can do statistical tests. We can see if the relationship between the predictors and what we're trying to forecast is a significant relationship. This is quite different from a lot of the models used today, where they're more like black boxes, where there's some hyperparameters and some parameters that have been selected, but there's no way to really interpret their meaning without quite a lot of extra work and visualization. Whereas a regression model, you can directly interpret the coefficients and understand some meaning for what the model is actually doing. We can also use regression models for forecasting. This is sort of a no-no when it comes to cross-sectional regression models, because a lot of our regression models use time itself as a predictor term. And when we're forecasting into the future, that time variable is inherently going to be extrapolating beyond the sample. We're going to predict things that the data used to train the model has never seen before. That's the nature of forecasting. Now, there's two types of regression models that are commonly considered. The first is simple linear regression models. This is when you've got a single predictor variable in a regression. And then second, we have multiple linear regression model. Fundamentally, these are very similar, and there's no difference when it comes to implementing these in R using Fable. You just add an additional predictor term, and suddenly you've got a multiple linear regression model. So perhaps a little bit of theory. If you're unfamiliar with how regression works, I imagine a lot of you have seen this before, so I'll go through this quite quickly so that we can learn something new with being the code. Simple linear regression, as I mentioned, has a single predictor variable called x. And this predictor variable, you can see here in the equation, has a linear relationship. So it's had a coefficient called beta 1, which is used to predict our response variable yt. Now, and we also have here a intercept for our model. Now, whenever we have a model and we're doing a prediction, we're going to have some inaccuracy. We can't expect our models to be perfect, and so we also have this epsilon t term, this error term in our model. And the epsilon t is going to be quite informative, and we're going to look at this quite a lot, a little bit today, but mostly on Friday with Bahman, because that's how we'll evaluate how successful our model is at capturing all of the information. We can use this epsilon t to check the assumptions of the model, which we'll talk about the assumptions of the regression model today. And we can also look at epsilon t to see how well we're able to predict the future. I'll bring up the chat so I can see if you've got any questions. I'll put this off to the side. Very good. Now, that's the model in principle. When we have some errors, this should have a hat on top of it. But in practice, of course, we don't know what the future will be. And so we make predictions, and therefore we don't know what the error term is. So our model for producing point forecasts, which we indicate with a hat, is using an estimated value of our coefficients beta 0 and beta 1. And these estimated parameters are from when we trained the model on our real data set. And we do this using the model function in R, just like Bahman showed in the previous session for the seasonal naive model, and also what we saw yesterday for estimating an STL model, which we use to decompose trend and seasonality. Different types of models have different capabilities. The STL model is able to decompose the data. The seasonal naive model that Bahman showed is purely a forecasting model. And the regression model helps us explain the relationships in the data and also predict the future with a forecast. So if we make a prediction from our model, in this case, it's a prediction of the in-sample data, which we call a fitted value, we can calculate the error as what actually happened. So the error at time t is what actually happened at yt, the current time, minus what we thought would happen, which for the regression model, these two would be identical. So we can calculate how well we're able to predict the data using a regression model as well. Now, you might have seen this visualization before. It's the visual equivalent to what that mathematics is describing. You might have some data shown in the black dots, and a regression model will fit a straight line. It's a linear model, so we get linear curves in the parameters. So when we have y against x. And recall our equation was y equals, or yt equals beta naught. You can see beta naught here. When x is 0, y appears to be roughly 3. So beta naught in this graph is roughly 3 plus beta 1 xt. And this beta 1 xt is giving us this slope, this red line here. And you can see it has found the line which follows the data as close as it can. You can see the cloud of dots is generally increasing, and that's why our red line also is increasing. And what we have here so far is my point prediction. Notice that I don't have any errors. If I put hats on everything, that's going to give me this equation. But in practice, to produce a model from it, which means that we'll get prediction intervals, a whole forecast distribution that Bahman was showing us in the previous session, we have some errors, epsilon t. And these errors are the difference between the predicted value in the red line and the actual value. And if we combined all of these together, we assume that epsilon t, try that again, we assume that epsilon t will follow a normal distribution. More than that, we expect that epsilon t will be centered around 0. It has a mean of 0. So most of the time, or on average, the errors are very small. And in fact, they'll cancel each other out and on average give you 0. That's an important assumption on our model because it's a biased, it ensures that our model is unbiased. The second assumption that we have for a regression model, and in fact all of the models that we'll look at tomorrow, is about the variance. We assume that the variance is sigma squared. It could be any variance. It could be very wide, meaning that we have high uncertainty. We're not very good at predicting. Or it could be very small, meaning that we're very confident and our model is doing very well at accurately predicting the values. What's missing here, or what's the assumption, is that, get my marker, is that it does not have a t subscript. We have a constant variance, which means for all of the x values, all of the time values, we assume that the variance of this observation, if we randomly picked it again, would be the same as this variation, We assume a constant variance, and you might know this as homoscedasticity. And on Friday with Bahman, we'll see how to visualize epsilon t and check that these assumptions are actually holding true when we use it on real data. It's important to do these checks because then we'll have confidence that our forecasts are correct. If we violate these assumptions, you might produce forecasts that have intervals that are too wide or too narrow. You might have forecasts that systematically over or underpredict the real value if your model is biased. So it's pretty useful and important to check these assumptions, but we'll do that on Friday. What's important for now is to understand that each of the models that we've introduced today follow this assumptions that epsilon t is normally distributed with mean 0 and variance sigma squared. Another assumption that we have IID. You might have heard this before. The important one is independent. The specifics of that we'll revisit on Friday. So the details of exactly how this model identifies what the best value for beta naught and beta 1 is. This is our estimated coefficients that I was talking about, beta naught hat and beta 1 hat, is using ordinary least squares. So we have the sum of the squared errors that I was talking about before. And our goal is to make this value as small as possible. And for regression, there's a neat trick that we can use. We can calculate this all in one step without optimizing it because it's got a closed form solution. But for the models that we'll see tomorrow, the ETS model and the ARIMA model, this requires some computational effort, some optimization. So those models that we'll see tomorrow can be better for time series, but the downside of them is that they're slower to estimate. The regression model is very good at producing forecasts quickly. So if you've got to produce a lot of forecasts and you don't have a lot of computational power, a regression model can be a good one to consider. Here's an example of ordinary least squares regression that you might have. This is predicting the consumption expenditure of the United States. So our Y variable that we're trying to predict is consumption. And this varies over time, which you can see in the orange line in the plot. And the way that we're going to predict this is using income. And this will be my predictor variable, xt. And you can see these two variables are actually quite similar. When consumption decreased, the orange line is now lower. You can see the blue line, our predictor, income, is also decreased. Similar, you can see the decrease here is reflected in both of the variables. So by plotting both of these variables together, either with a time plot, or perhaps better would be a scatter plot of consumption on the y-axis and income on the x-axis, we can see how well these variables will be at predicting the variable that we're interested in. So here's the scatter plot between those two variables. You can see that we've got a fairly broad cloud of values. The signal here is not very strong, so we expect to have pretty wide forecast intervals. But generally, there seems to be a positive relationship, which you can see with the blue line. This is a least squares line that I've added to the plot. This is essentially the regression model that we're going to estimate. So I want you to try this with me in R. I'll put the code for this into the chat as well. So I've copied across some of the code from Bahman, which we'll look back on later. But we're going to write a new model now, which instead of using a seasonal naive model, we're going to use the TSLM model. TSLM stands for time series linear model. The time series part adds a few features, a few predictors that you can use specific for time series that we'll see later, such as adding trend and seasonality to the model. The data set that we're looking at is US change. It is quarterly indicators of the economy. And notably, they're percentage changes. So usually you'd expect these to be a couple percent. And sure enough, when we plotted the data in the previous slide, you can see these values range from -2% to +2%. They don't change very often. Don't change by much. Now, to specify the regression model, just like every other model that we've seen so far, like seasonal naive, we need to say which variable we want to predict. And that goes on the left side of this formula. So the tilde, like we saw yesterday for the STL model, the tilde represents a formula in R. On the left-hand side of that, we have what we're trying to predict. And on the right-hand side, we have how we're going to predict it. So yesterday we saw how to add trend and seasonality to a STL model. This time we're adding income as a predictor of consumption in our TSLM model. If you run these two lines of code, we've got a new function here called report. This gives a nice table of results, a summary of what the model is doing. remember that TSLM is an open box. We can look into it and see exactly how it's using income to predict things. I see an error reported in the chat. Could not find the function pipe. That would be because you've not loaded in the FPP3 package. So make sure you run this line of code first before you, that will give you access to the dataset and all of the models that we need for today. So a pretty big advantage of regression model, in fact, two big advantages of using regression models can be already seen. The first is that we're able to use extra information that might be available to us in order to predict consumption. The seasonal naive model, for instance, could not use any extra information. If I tried to use beer against tobacco, this wouldn't work. The seasonal naive model does not work with extra information like this. The TSLM model is unique for the models that we're going to look at this week because it can use extra information. The other additional nice thing about the regression model is this table of coefficients that we can get. These table of coefficients allow us to interpret each of the parts of the model and what it's doing. We can see that the intercept for this model is roughly 0.54, which says that if all other variables, if income changed by 0%, then we expect consumption to still increase by about 0.54%. What is also nice is the estimated coefficient for income. What this says is if income were to increase by 1%, we expect, on average, that consumption, put a capital I on income as well, we would expect that consumption would also increase by 0.27%. Where did I get this 0.27%? That's from this estimated coefficient. What this says is if income were to increase by 1, remember our equation for this, I'll write that out. Our equation for this model is consumption at time t is equal to an intercept, beta naught. Now this intercept has the value 0.54 plus my intercept, my coefficient, beta 1, for income, my predictor variable. And we also have some error. Now the coefficient for income is 0.27. So this model, the math here, allows us to interpret what happens when income changes. What happens if income were to increase by 2? Then consumption would also increase by how much? Pop your ideas in the chat. Think about how these two variables are multiplied by each other. Okay, I've got one direct message. You've got the correct answer. Well done. I'll give other people an opportunity to try to anticipate what changes in consumption. Okay, a few more correct answers coming in with direct messages. Fantastic. You've all got the right idea. So we have an increase of income by 2, and the coefficient for income is 0.27. So we would expect consumption to increase by 0.27 multiplied by 2, the change in income, which is equal to 0.54. How do we interpret this? What does this mean? Well, What this says is, I'll copy from up here, if it was to increase by 2%, if income were to increase by 2%, on average, we expect that consumption would increase by 0.54%. So this allows us to understand what this model is doing and get more understanding of the data itself, how these variables relate to each other. Okay, moving on to multiple regression. Multiple regression is essentially the same, except we've got multiple predictor variables. So I'll go through this a little bit quicker. There are some concerns. You can always add more predictors, and you might think that you're making a better model as a result, but that's not always the case. If you add lots and lots of predictors, or some predictors that are very similar to the response variable, you can run into two problems. First of all, you can overfit the model, and this is particularly problematic when it comes to forecasting because we're extrapolating. We're trying to predict beyond the training data into the future, and overfitting can really make your forecasts terrible. They can make it go in the complete wrong direction as soon as you go outside of the sample training data. The other problem is multi-collinearity. What this essentially means, and I've got some slides coming up for this, is that the values of X are very similar to the values of Y, the thing that we're trying to predict. And this causes various statistical estimation problems. Our hypothesis tests will have issues, and our forecast intervals will be unreliable as well. So when you add variables, you want to make sure that they are meaningful, not just an extra information because you have access to it. Okay, here's the mathematics for multiple linear regression. Previously, for simple linear regression, we just had this bit. But now for multiple linear regression, we have several X variables, which each have their own coefficient for the model. Now, we can interpret each of these coefficients just like we did before for simple linear regression. There's one slight difference, is that we need to say holding all else constant. We need to assume or specify that if X increases by 1, then we'll have a beta 1 increase in YT only if there is no change to all of the other X variables. You can also read off multiple coefficients and say if x1 was to increase by 2, but x3 decreased by 1, you can calculate the linear changes in all the coefficients and calculate the total change in yt. So that's why working from the formula here, the mathematics, is a nice way to understand how the coefficients relate to each other and anticipate changes in the data, the predicting variable yt, sorry, the response variable yt, based on changes in all of your predicting variables. Just like before, if we wanted to find out what these optimal values are for the betas, our coefficients, we use least squared errors, ordinary least squares. So squared sum, which is equivalent to this one. Remember, ET is equal to YT minus Y hat T. Y hat T is equal to, let's use a different color. Y hat T is equal to my model that I had for the regression, multiple linear regression. YT is right here. So you can see these are the same. We calculated ET from the actual values minus the predicted values. So if you've seen regression before, that would be hopefully no surprises. You just use extra information to predict values within the sample size. However, when it comes to using linear regression for time series, the TS, when we look at TSLM models, there's a couple of useful predictors that we want to use. The first is a linear trend term, and this is the simplest of the two. A linear trend term is a special type of X variable where it's simply the time index. And the time index starts at 1, and it simply counts up by 1 value until you reach the end of the data. So if I had a model, if I drew my line plot that looked like this, including, so this is time and this is y. If I did a regression of yt equals my intercept plus my slope for my trend, notice I'm not writing, I could write xt, but of course xt is equal to t for a linear trend. That's the definition of a linear trend term. So I can simply replace xt with t. What this will look like for my time plot here is a straight line through the center of the data. So that's a pretty good way to include a trend. It's not perfect. Notice that the pink line that I've drawn, it has a little bit of a curve to it. This is an exponential trend. It's not linear, it's not a straight line. And the models that we'll see tomorrow are better suited to forecasting sloped trends like this. The second type of pattern that we might like to include in a regression model is seasonality. So we talked yesterday about the different patterns that are commonly observed in time series. We talked about trend, seasonality. We also talked about cycles and outliers and weird observations. Linear regression is good for linear trend and regular seasonality, additive seasonality, because it's an additive model. You can use a log transformation, just like we did for STL decomposition yesterday, in order to work with multiplicative seasonality using a regression model. But a regression model is not very good at capturing time series dynamics, the autocorrelations that we saw on day 1. So as a consequence of this, regression models cannot do very well at capturing cyclical patterns. Trend and seasonality, no problem. Even effects like COVID, additional information we could bring in saying that there was a pandemic, and then the model can learn that we have less demand or the response variable is lower whenever we have another pandemic in the future. But this type of model is not good for capturing cycles. So how does the regression model capture seasonality? It does this using dummy variables. Has anyone heard of a dummy variable before? Okay, got a few private messages as well. A couple of people saying that they have heard of it. Does anyone want to offer an explanation? What do you think a dummy variable is? And how might we use seasonal dummy variables to describe seasonality? Now that you've put your thumbs up or said yes, put you on the spot. Have a go. Okay, Henok suggests a sine or a cosine pattern. That's actually an even better way of capturing seasonality. I don't think we've got it in this course, but it's called Fourier terms. I'll make sure to show you how that works. But sine and cosine functions are really interesting because they're naturally periodic. They're naturally seasonal because they repeat over a certain period of time and they always have the same shape. So sine and cosine patterns are really powerful for capturing seasonality in a regression model as well. Okay, there's a few other suggestions. A dummy variable has a value of 1 if it's yes, 0 if it's no. That's exactly right. And another suggestion is that we have a separate indicator, a separate yes or no for each of the seasons. And that's exactly right. So for seasonality, we create several variables for our regression model for each of the values in a seasonal pattern, each of the time points, each of the seasons in a seasonal pattern. Lots of ways to describe that. So we might have dummy variables for Q1, Q2, Q3, and Q4. And let's say we also have time, which is now going to be 2020 Q2. And then we have another row that is 2020 Q3. What would my dummy variables be equal to for the first time point? So Q1 will be 1 if time is in Q1, but we're currently in Q2. So this would have the value 0. The second dummy variable, Q2, would be 1 because the first time point, this one here, is currently in quarter 2. So this dummy variable, this indicator variable, now gets activated. Yes, we are currently in quarter 2, so we have the value 1. Q3, we're currently in Q2, so this indicator will be disabled. So we'll have 0 for Q3. And I hope you get the idea. Q4 is also going to be 0 because we're not currently in Q4. I want you to put in the chat the next row of the data. What would be the indicator variables for if we're in 2020 Q3? Fantastic. Looks like everyone's getting that right. So we would have 0 because quarter 1 is not activated in quarter 3. 0 for quarter 2 this time because we're currently in quarter 3. And quarter 3 would get activated. This one's now turned on because we're currently in that quarter 3. And lastly, Q4 would be 0 as well. So how do these dummy variables add seasonality to my model? Well, if I extend my model, let me redraw everything now. So now I've got some data which has seasonality and trend. If I just did this model here, beta 1 with trend, I would get a straight line through my data. So this isn't going to capture my seasonality. I need to add in my seasonal dummy variables in the model, and we'll see how that adds a seasonal pattern into my predictions and my forecasts as well. And we do this using multiple linear regression that we just learned about. So currently we've just got one predictor. If I add on each of these dummy variables, so we have, let me rewrite this with some more space. Yt is equal to beta naught plus beta 1 xt. That's what we had before. But this time we're going to add on plus beta 2 as an indicator if we're in Q2 at Q1, sorry, at time t. Let me write that a bit better. Q1 at time t. Now there's lots of ways that you can write these variables. They're just names for things. But we're also going to need dummy variables for all of my other quarters in the seasonality as well. So beta 3 for Q2t plus beta 4 for Q3t plus beta 5 for Q4t. See how I've added all of my dummy variables into the model? Now, when we do this, there's such a thing called the dummy variable trap. And as a result, in practice, we don't include one of these from our model. The reason being is that beta 0 is essentially a column of ones. It's always activated. Sorry, not beta 0. There's technically a x0 coefficient here, like a term, a predictor of the model. And this x0 term is all ones. What happens when I add together all of my quarters, all of my dummy variables? So we have Q1 plus Q2 plus Q3 plus Q4. Then this would equal 0 plus 1 plus 0 plus 0 equal to 1. The next one will be equal to 1. And the combination of all of my dummy variables for my seasonality, if I add them together, I also get a column of ones. So in a regression model, it's not allowed to have two variables that are identical. It's similar to the multi-collinearity problem, but in the predictors. And the way we get around that is to remove one of these variables, one of the seasons. And that makes no difference to the model. It's not like we're unable to predict Q4. It's just that we know what Q4 is by calculating the intercept minus all the other quarters. So all the information is still there. So let's see what happens, how we're able to get my seasonal pattern. So let's say this value is starting in Q1. And Q1, the intercept, the coefficient for Q1t is negative 1.2. The coefficient for Q2, I'm going to say, is positive 2.3, and so on. If I'm trying to predict this first value, I will have my mean of the data. Let me draw that. Sorry, just the trend term that we had before in blue that would go through the middle. That's what we saw earlier. But now this dummy variable for Q1 is going to change the prediction a little bit because we're currently in Q1. It's going to decrease my prediction by 1.2. And that's what changes my prediction of Q1 to actually be right on the seasonal value. What happens when we have Q2? So now Q1 will have the value 0. So this is doing nothing. Q2 will have the value 1. So now it's activated. It's going to increase the base prediction, the pink linear line, by 2.3. So it's going to drag up this value and result in my peak. And then we do the same for Q3. Q4 is not needed because it's already in the intercept. And as a result, my forecasts are now seasonal because these dummy variables are going to activate and deactivate throughout all of time, slightly adjusting my predictions up and down to give me the seasonal pattern. I think this is a good time to ask if you've got any questions, because that's the main part of the theory for the regression models today. And then we'll see a few examples of this and produce some forecasts from these models. The other really cool thing that we can do with regression that we couldn't do with the benchmark models that Bahman introduced earlier is that we can include both trend and seasonality in a model. The seasonal naive model that we're looking at in the previous session can only handle seasonality. It can't include a trend. And the random walk with drift method only produces a trend. It doesn't produce any seasonal pattern. So by using linear regression, we're able to include as many predictors as we like, including both trend and seasonality. Okay, can we talk about how we estimate the beta 2, beta 3, beta 4, all of these coefficients for or the quarters? Yes, it's the exact same way that we estimated the coefficient for beta 1. Let me see if I can hide. Okay, maybe I'll be able to get them back later. But this equation here, where we had the errors, the sum of squared errors that we're trying to minimize, now on the right-hand side, all of these extra x terms, xk, here we just put in our dummy variables. And by minimizing this equation, trying to minimize our errors by choosing different values of beta 1, beta 2, beta 3, all of the coefficients for my seasonality as well, it's going to work out what the best possible value is for our seasonal coefficients and our trend coefficients all at once in order to get us the best possible model in linear regression. So essentially, it's the same way as before. The dummy variables are no different from the trend coefficients or my predictor variables. We're just trying to minimize the sum of squared errors. And there's some math in the textbook, the FPP3 textbook that we can link to for exactly how that is done. It's some matrix algebra. There's another question, a very insightful question. Are we using Q4 as the base or reference time? And that's correct. Let me see if I can bring back the notes. Yes. So if we're not including Q4 at all from the model, then the assumption, the way that the Q4 comes in, is that Q4 is always on. And it's absorbed in the beta naught intercept. And what this does is that now all of my coefficients, say Q1 I said was negative 1.2, this is now saying that it's going to be 1.2 less than Q4. Because Q4 is now always on. It's part of the intercept because I've removed it from my model. So this is important to consider when we interpret the coefficients, and I will remind you of that when we look at this in R. You can choose any, there's another question, do we have a certain rule or criteria to select the base year? It makes no difference which one you choose. The results, the forecast will be identical. It's just when you interpret the coefficients, you'll need to know which one hasn't been included so that you can accurately interpret the coefficients. Okay, I think I'm going to skip this example. This is the same US consumption expenditure example that we looked at before that had consumption and income. But it's just showing that we could also include production, savings, and unemployment all in the same model, which is done again with the TSLM function. We just add, previously we had consumption and income. You can also add all of the other variables that you like, and it will automatically produce multiple linear regression. So you can see now we have multiple coefficients for those terms as well. And ideally, by including more of these predictions, more of these predictor variables, we'll have a more accurate fitted value. So in orange here, we have the real data, and in blue, we have our predictions of that data. And you can see our predictions are quite accurate. This is a sneak preview of what we'll see on Friday with Bahman. This is a useful way to look at the residuals, those epsilon t that we were looking at before. And the main thing that we want to check here is the assumptions on our error term. That it's IID, normal, 0, sigma squared. So you can see the normal distribution from the histogram, the mean 0 from the center here, the variance from this residual plot, and the independence from the ACF plot. But I'm not going to go into details on that because Bahman has a whole session set out on the last day for this. I'm also going to skip through evaluating, but I will talk a little bit about selecting predictors. And tomorrow, when we look at ETS models and ARIMA models, the method that we can use to select predictors for a regression model are also used quite a lot for the models that we'll see tomorrow in a way that automatically selects the best model possible for your data. So there's two ways that we could choose the best model when it comes to regression. The first of which is called R-squared. Has anyone heard of R-squared before? Maybe you can explain what it is if anyone's brave. Otherwise, put your thumbs up in the reactions if you've heard of the R-squared value before. Very good. It looks like everyone that knew what regression is has also heard of R-squared before. It's very common to look at the R-squared value when you do a regression. And in the chat, there's a great explanation. How much variation in the response variable is explained by variation in the predictors. So R-squared is calculated like so. You can see the math here. The numerator here is a type of variance. There's variance in the predicted value. Remember, y hat is a prediction. And the sum of the minus and the squared, this is just the way that you calculate a variance. And on the denominator, what we have is the actual values. So this is the variation in the actual data. So the R-squared, also known as the coefficient of determination, is the variation in the predictions relative to the variation in the actual data. And the idea of R-squared is that we want to make it as close to 1 as possible. So what we can do is add additional predictors, and what you'll find is that the R-squared increases. There is a problem with that because I could add any predictor. I could add completely irrelevant things to my model, and I will still get a better R-squared value. And this is why it's common to instead use adjusted R-squared. It looks very similar. In fact, we've got the exact same R-squared in here as before. That's sum of the variance, so the other variance. But what we've got now is an adjustment for the number of parameters that we've added in our model. So K is the number of predictors. Another way of describing this is degrees of freedom. The adjusted R-squared considers the degrees of freedom used up by the predictors in the model. And what this solves is that we can't just keep adding additional predictors in the model and improving R-squared. If I add a predictor that actually is irrelevant and doesn't actually explain anything, my R-squared, adjusted R-squared, will go down, indicating that this variable is not worth including in the model. Another type of statistic that we can use to choose the best model is Okeh-Ikey's information criterion. And this uses the likelihood function, which is another way of describing how likely an observation was to occur if it came from the model that we described. So roughly saying that's how good our model is at describing the data. And this AIC term, Okeh-Ikey's information criterion, also has K in it, which means as we add more predictors, the AIC is going to get worse. It's pretty similar to the adjusted R-squared that you might have heard of before, but it's even harsher when it comes to adding additional terms. So it's a heavier punishment for adding irrelevant variables. And we tend to prefer using Okeh-Ikey's information criterion for forecasting. Partly because when we're extrapolating, when we're producing forecasts of the future, it's a lot more sensitive to including predictors that only help a little bit. We want to only include the most relevant variables. So when it comes to selecting a model and choosing which variables are worthwhile including in the model, a good approach is to try to minimize this statistic, the AIC. And when I show you the results in R, we'll see how to look at the AIC and compare if including or excluding a term in the model improves or worsens the model itself. There's also a corrected AICC for small sample sizes. We also tend to just use AICC. There's another question in the chat. Should we include one predictor variable at a time, stepwise regression, to determine whether to include a variable or not in the model? Yes. So the same variable selection processes that you might have heard of before for cross-sectional model selection can also be used for time series linear regressions. So you can add one extra term at a time and see if the adjusted R squared, or even better, the AICC term, after Ike's information criterion corrected, gets better or not. So there's some slides on this. Best subsets regression is one way where you fit all of the regressions and then remove them bit by bit to choose the best model. And then backwise, stepwise selection is another process, removing one at a time and keep going until the statistics, cross-validation or AICC or adjusted R squared doesn't go any better. What you're describing there is actually called forward stepwise selection of a regression model. Any of these will work okay. Okay, I think it's time for us to look at some of this in R, and then we'll see how far we can get with the rest of the slides. So I want to go back to the OSBEER dataset that Bahman was talking about. So here's the code from the first session from today. Bahman, perhaps you could explain the likelihood to that question as well, if you're here. So Bahman showed a model for Australian beer production in the year 2000s. This data looked like this. So clearly lots of seasonality, maybe a bit of trend, but it looks fairly flat. So it'll be interesting to see if the model, regression model, wants to include a trend or not. So what we can do with our model is, Bahman showed you how to estimate multiple models at the same time. So where he had seasonal naive of beer, I also want to add multiple linear regression using the TSLM function, where I predict beer using both trend and seasonality. So the trend function will add in a linear trend, that T term that we talked about earlier, and adding season will add in dummy variable seasonality. Then I need an extra bracket to close that off. And now in my model table, you can see I have two models. One, the seasonal naive model that Bahman created, and second, the multiple linear regression model that includes trend and seasonality. The bits on the left here, S-naive and MLR, these could be whatever you like. These are just the names of the variables, names of the models that have been given the table. Now, Bahman also showed you how you can produce some forecasts from these models. So it works exactly the same as before. If I wanted to forecast 2 years ahead, I can use the forecast function and specify the horizon being 2 years ahead. Or for quarterly data, this is 8 observations, 8 steps. And then I can plot these forecasts using the original data. I thought I could. What's going on here? I'm using OSBEER. this should be my fitted models. So I use my Mabel, produce some forecasts from my Mabels, which gives us a fable, a forecasting table. And this time the fable has two models in it. You can see model is a key variable containing two different sets of forecasts. But firstly, we have the seasonal naive forecasts and the normal distribution from them. And second, we have our forecaster and the multiple linear regression model, which are also normally distributed. And remember, autoplot's pretty clever. It knows how to produce the right plot automatically based on the type of data it's using. And because we're giving it a forecast, if I use autoplot, I get a plot of those forecasts. Well, it looks like there is a bug. I think my versions of the ggdist package is out of date. Let me update that. I'll actually update the ggplot package. I don't usually work in RStudio anymore. I've switched to Positron, so some of my packages are a bit out of date here. So if you get black boxes around this, the solution is to update the ggdist package. Okay, while that's running in the background, the lines themselves still look correct, so we can have a look at them. Just try to make this plot a little bit bigger for us. But the R console is busy. But what you can see, I hope, is the forecasts between seasonal naive and multiple linear regression look fairly similar, right? The point forecast, the shape, they both capture the seasonality. One of the big differences that I can see between these models is that the regression model appears to have much narrower intervals than the seasonal naive model. And narrower intervals suggest that my errors are smaller. My model is more confident at its predictions. There's the zoomed in version. Which of these two forecasts do you prefer? Maybe you could put in chat MLR or S-naive. Which model do you think is producing the better forecast? Okay, it looks like everyone is saying MLR. And for this example, I would agree. You get some hint by the size of the intervals, but it can be a problem if your intervals are too small as well. So you want the intervals to accurately reflect the uncertainty in the data. Sometimes the peak, the seasonal pattern, is much lower than other times. And we want to make sure that our intervals can accommodate that. So maybe it didn't increase as much as we expected. Maybe it's a bit lower down here. Because it's happened in the past, it could happen again in the future. It's not very common. It only dropped that far once. And so these intervals probably are reasonable. They're not so wide. The blue intervals from the seasonal naive model are incredibly wide. And this is wider than any of the values and unexpected changes that we've seen in the past. Notice how the bottom range here hasn't gone below 370, whereas the seasonal naive model is allowing it to go lower than the multiple linear regression model. So there's some hints. But the main takeaway from that is that we don't know for sure yet. And on Friday with Bahman, he'll teach you about how to evaluate the accuracy of forecasts. And there's a few techniques that allows you to identify which model is better, both on predicting the past and predicting the future. Another way is to evaluate the assumptions of the model with that plot of the residuals that we briefly saw earlier. Bahman will go into more detail on checking the assumptions of models on Friday. Okay, I want to finish up by talking a little bit about how we forecast with regression. We've just seen one example of how we produce a forecast. But with regression, remember that we can also use additional information. We predicted consumption using income, and maybe we want to forecast the future values of consumption as well. So there's two types of forecasting that you can do with regression models when you have additional predictors that you need to also have. Ex-ante forecasts are made using only information that you already know. That you don't yet know. So in this case, we also need to forecast the predictors. So when I'm predicting consumption, using income, if I wanted to forecast the future of consumption, then I also need to know or predict the future values of income as well. And that can be difficult because sometimes it's just as difficult to predict income as it is to predict consumption. Or in general, it can be just as difficult to predict the predictors than it is to predict what you're actually interested in. So this can be limiting for what regression variables you actually want to use. Stuff like temperature is a good one because we are usually pretty good at predicting temperature a few days ahead. And we have a rough idea of what temperature will be in summer and winter many months ahead. So temperature can be good to include, but a predictor like income is pretty hard to predict. It's probably just as difficult to predict as consumption. That doesn't mean that you can never use income or that model, and that's because you can also produce ex-post forecasts. And ex-post forecast means that you're now in the future and you're looking back on the past. You now know what the actual values of income were, and you can use them to study the regression model, just like we did when we interpreted the coefficients. The reason why we're able to produce predictions before with our regression model, this model that used trend and seasonality, is because we know exactly what the season will be in. In 2010 Q1, we're going to be in Q1. In 2020 Q1, we're going to be t time steps into the future. We can calculate precisely these values into the future, and so they're also perfectly reasonable to use in a regression. We don't need to forecast these because they're very well known. Now, just because we don't know the future values of income or the future values of the temperature or anything that we don't know for certain doesn't mean it's not useful for forecasting either, because we can also assume what possible values of them could be in the future. What if tomorrow was 10 degrees warmer? What if income dropped by 2%? How would that affect consumption or ice cream sales or tourists or electricity demand? And this is really powerful for decision making, because remember, your forecasts are only really useful if they produce value for making decisions. If you're just producing forecasts that are accurate, that draw a line on the screen that you think is going to be matching the real data in the future, well done. But it's not really making any value because no decisions are made but from it. Scenario-based forecasting, where you can say, what if temperature was to drop by 10 degrees? What if people were to move away from Australia? If maybe people were migrating to New Zealand, how would that affect the GDP? How would that affect our hospitals? For COVID, I was doing quite a lot of scenario-based forecasting for the government. They wanted to know, what if we required people to wear masks? How many people would be in hospital? Because they were worried that we'd run out of spaces in our hospital to take care of the sick. So by giving the government different scenarios for policy decisions, if we wore masks, if we prevented people from traveling a certain distance, allowed the government to make decisions on policy to ensure that we don't run out of spaces in the hospitals. So scenario-based forecasting is one of the really powerful techniques that you can use with regression. This is how you do it. So let's go back into R. And we're going to go back to the US change example, the model that we looked at for consumption and income. You can look at this slide to see all the extra information for savings and unemployment. Hold on. Bahman has also put a great link in the chat from the textbook on causal regression. This has a lot of useful information on how to do scenarios as well. So we're going to go back into R, and we're just going to focus on consumption and income like we had before. Now, we're not going to worry about savings and unemployment, but if you're interested, you can look at the code here on your own time. So I'll copy the model from earlier. So just so that you can see it, we had fit of consumption. I'll put this into the chat so that you can try this yourself as well. If I were to try to forecast this 2 years ahead, you can see it doesn't work. I just get an error, and it tells you that income is not found, right? That's what we're trying to predict with. And it's saying unable to compute from the data set, does your model require extra variables for forecasting? And in this case, it does. We're using income, so we need to provide future values of income to produce a forecast from this model. The way we do that is by setting up some new data. The new data function can help us produce this, and perhaps we want to produce forecasts for 8 steps ahead. Not fit consumption, sorry, US change. And what this new data function does is that it sets up the time indexes for the next 8 steps. And you can say, I want to predict 4 years ahead, 16 quarters, and then we get a bunch more predictions. So this new data can also be used inside the forecast function. So I'm going to call this the future changes. And when I forecast, I provide the future changes. And I still get the same error, income not found. But this is where I can add in scenarios for what happens to if income were to be zero change in the future. Maybe we have the status quo. Income is always 0% change. Now I'm able to produce some forecasts under that scenario of income being 0. And I can plot them with the original data. So that would happen if income never changes in the future. What if income were to increase drastically? Income is now 2% change increasing every year. Now you can see that my forecasts are higher than they were before. What if my income was +2, dropping down to 1, 0, back up to 3 even, a massive year for income, -1, a crash after the boom, down -2, and I'll just fill in the extra ones with a bunch of random numbers. I'll need 10 of them. So I can come up with some predictions, some scenarios of what will happen in the future for income. And you can see I get forecasts as a result of all of these different incomes that I'm expecting in the future. So these can come either from predictions of another model or from assumptions or tests, hypotheses, scenarios for what might happen next. Right? Maybe there's a big crash for the pandemic and income dropped by 10% and then down by 20%, and then it went back to normal. You can see a big crash in the forecasts. Now, you do have to be a little bit careful with the scenarios here for the purpose of extrapolation. In this case, the data never had any information of what happens if income were to drop by 10% or 20%. In the past, we've only seen income drop by at most 3%. So we have no idea what will happen if it dropped by that much. we don't have the data to support that. So you do need to be a little bit careful about how much you vary these and make sure that you've got enough data to support the changes that this forecast is suggesting. Okay, we're out of time, so I'm just going to skip through the rest. Bahman has provided some extra information from the textbook about scenario modeling, but also causation. A lot of what we're doing here is more about correlation than causation. There's other models that you could use for identifying causation. Here's an example of correlation that looks very similar. These two lines are very closely overlapping, but they're completely unrelated. Number of people who have drowned by falling into pools is not caused by Nicolas Cage appearing in a film. They're completely separate, and this is entirely coincidental. So this is a correlation, and you have to be careful not to treat this as causation. It's not that income dropping by 2% causes consumption to decrease by 0.5%. It's just that there's this correlation between them. So we expect it to drop, but we're not for sure if that's why it's dropping. Okay, so we've talked about dummy variables. Go through a few extra useful predictors to finish up. Dummy variables are the yes/no variables that we talked about before, and we use this for seasonality, but you can also use this for other things, such as pandemic. Yes, a pandemic is on, so we'll drop our forecasts a lot. No, a pandemic is not on, we'll go back to normal. We talked about the dummy variable trap. We talked about seasonal dummy variables. You can also use dummy variables to remove outliers by having a dummy variable for each outlier. And also for holidays. You can have a dummy variable being 1 if it's during a holiday. So maybe it's during Christmas or New Year's, and you can have a dummy variable for each of these holidays. You might also have a step change, maybe a policy change. We saw this in the ANSET data. Let me bring that back up. So we had ANSET, and then I filtered the data to just be Melbourne and Sydney. And then I plotted the passengers. We talked about how there was a structural change where they redefined what economy class tickets were to make business class more attractive. They made it cheaper. You could incorporate this in the model using dummy variables as well. You can say a policy change happened between this time period. So then we'll turn the variable on, the dummy variable on. Everywhere else, before and after, would have a value 0. You could use dummy variables for this too. You can also use a dummy variable for the strike to remove that or to account for that in the model. Okay, there's a bit more that you might be interested in, but we are out of time. So what you can do with this actually is if you go to the AFRICAST website, if you are interested in interactions with variables or nonlinear effects, or perhaps lagged effects. Lagged effects is a good way of incorporating extra information without needing to predict it. We have the recording from last year that you're welcome to watch. If you go to resources, you can click on recordings from previous years, which you'll see has the 2024, so that's day 2. On day 3, it'll look the same. We'll have the recordings from last year available in this drop-down box. And I'll put the recordings from today up the top. Okay, I've got to get going, but perhaps Bahman could answer a few final questions. But that's all I have for you today. So thank you very much. I hope you enjoyed it, and I hope you make the most of the mentor sessions this afternoon. There's another great set of exercises. Next week, we'll be looking at ETS and ARIMA models, which are really good at capturing trend and seasonality, especially when the trend and seasonality changes over time. So we saw that the linear model wasn't able to capture when we had a sloped trend. The regression model cannot do that because it's linear. We will see ETS models and ARIMA models tomorrow, which can handle changes in the trend and seasonality. Bahman, any final words?
Thank you, Mitch. Thanks a lot. Yeah. So I will just stop the recording.
Fantastic.